Convolution is a new operator that is really helpful for finding inverse Laplace transforms. So this new operation is defined like this. We have some f of t, and the operator we use is a little star symbol. G of t is defined to be the integral from 0 to t, g of t minus tau f of tau d tau. Now I'm using the Greek letter tau here. If you don't like it because it looks too much like your t's, feel free to use any letter that you want, but tau is the traditional variable for this transformer, this operator. So if we try to do the Laplace transform of this, and it's not that hard to show, what you end up with is just the Laplace transform of each one of those functions, f of t, times the Laplace transform of g of t, or another way of writing that is big F of s times big G of s. Now the good news for this is actually going the other way, which means the inverse Laplace transform of two functions multiplied together, as long as we know the inverse of each one of these, well, all you gotta do is do the inverse Laplace transform of each one of these and plug them into this integral to get your answer. Now you still need to do this integral, which can be tedious sometimes, but it is generally just a straightforward integral to do. So to do this, once we have two things multiplied together, we say, can we do the inverse Laplace transform of each one? If we can, we find the inverse Laplace transform, plug it into this, and then do the integral. So let's say that we were looking at, so if I said find the inverse Laplace transform of 1 over s squared s minus 4. Now if you notice, we could rewrite this like 1 over s squared times 1 over s minus 4. Now if you've been keeping up with all the work, you can see that each one of those would be very, very simple inverse Laplace transforms on their own if they weren't multiplied together. But using convolution, we can do it like this. It doesn't matter which one you call which. Let's call f of t the first one, which would be the inverse Laplace transform of 1 over s squared. And g of t, we might actually change these labels in a second. The inverse Laplace transform of 1 over s minus 4. All right, we know what this is. This is just f of t, that's just t. And g of t over here, let's see, that would be e to the 4t. Now what we got to do to come up with this inverse Laplace transform is take these two functions and plug it into this definition. Now the good news, it doesn't matter which one you call f and g, because I randomly called f and g over here. Now generally you want to pick g to be the easier of the two functions, or the more simple one, because we got to plug in this shift to it. This one actually wouldn't matter either way. I'm actually going to let this one right here, hold on. All right, I'm actually going to switch the labels here because I actually think that this one would be a little bit easier to be g. So I'm going to go ahead and say, let's let g of t be t and f of t be e to the 4t. Basically, it doesn't matter which one you call which. All right, so just to give me some room, I'm going to start back up here. Let's see, so I get that out of there. So the inverse Laplace transform of this will be the integral from 0 to t. Now I'm going to go into our function g, and everywhere there's a t, I'm going to put a t minus tau. And then I'm going to go into f, and where there's a t, I'm going to put a tau. All right, let's go ahead and distribute this. This is 0 to t, t e to the 4 tau d tau minus 0 to t tau e to the 4 tau. This first integral is very, very easy to do because t is a constant, so you can pull that out front if you want. E to the 4 tau minus. Now this one we're actually going to have to do by parts, so let's go over to the side here and see if we can write this out. Tau. So if we let u be equal to tau, dv would be everything else for tau d tau. du is just d tau, v is 1/4 e to the 4 tau. All right, so this first integral is very, very straightforward. That's just 1/4 t e to the 4 tau. Now, of course, we got to evaluate this from 0 to t. but I'm going to wait till we get everything done and we'll evaluate it all from 0 to t. So by parts is uv, so that's 1/4 tau e to the 4 tau minus the integral of v du. So that's 1/4 e to the 4 tau tau. All right, that last integral right there is very, very easy to do. So let's go ahead and just distribute t e to the 4 tau. 1/4 tau e to the 4 tau plus 1/16 e to the 4 tau. Now we still need to evaluate this from 0 to t. All right, top endpoint, when we put in the t, remember we're plugging in for taus here. So it's 1/4 t e to the 4t minus 1/4 t e to the 4t plus 1/16 e to the 4t. Minus, when we plug in zeros, zeros for tau, this is going to be 1/4 t, that's e to the 0 or 1, so that's just 1/4 t. Plug in 0 for tau here, this term goes away. Again, when we plug 0 into here, the exponential becomes a 1, so that's just 1/16. So simplifying this, notice the first two terms are going to reduce or cancel, so that cancels. So I get 1/16 e to the 4t minus 1/4 t minus 1/16. All right, so we can bring this back up here as our result. So the inverse Laplace transform of this, 1/16 e to the 4t minus 1/4 t minus 16. Okay, so there you go. So convolution, other than having to get through an integral, is a very, very useful technique for finding the inverse Laplace transform of things. Now, we could have done this one another way. We could have done this by partial fractions. Would have been about the same amount of work. Maybe this one actually might have been a little bit more for this one. But this is a great technique to use, so make sure that you follow how we did this. All right, let's take a look at one more thing that we're going to need for our future. And it is, how do we take the Laplace transform of a derivative? Okay, now what I mean by that is, how would you do the Laplace transform of the derivative of a function? I'll put an X there. Kind of like this. If I say, what's the Laplace transform of y double prime, right? A second derivative. Well, what you would do is you'd actually just plug that into the definition of our Laplace transform. You do it by parts, and it ends up giving you this kind of recursive relationship. Here's what happens. Now, this is the nth derivative of some function. The first term is always going to be s to whatever that power is. So if that's the fifth derivative, this would be s to the fifth times the Laplace transform of the function itself. Now the rest of these are going to be minus, and here's the pattern. The power on s counts down. So the next one's going to be s to the n minus 1, s to the n minus 2, so on and so forth. And then, remember, our Laplace transform of some function is defined to be the integral from 0 to t, e to the negative st, f of t dt. Think about when you actually do this. You plug in the top endpoint minus the bottom endpoint. Since the bottom endpoint here is 0, we're going to get this function evaluated at 0 as we go along. Well, the function and its derivatives. So, when we start with the power of s, it's going to count down. The function derivatives count up, and we're going to be evaluating these at 0. So it's going to be f of 0 minus s to the n minus 2, and then the derivative counts up, f prime of 0. Power of s counts down, derivative counts up. Now this is going to keep going until we run out of s's, and the very last one's going to be f to the n minus 1 derivative at 0. Basically, you're going to end up one derivative short of what you actually started with. So let's just take a couple real quick looks at this. Here's what we mean. Let's do the derivative of y double prime. So since the derivative is 2, we're going to start out with s squared times just the Laplace transform of y, whatever the function y is. Now, all the rest of these are going to be minuses. The power of s counts down, so that's going to be s. The derivatives count up, so that's going to be y of 0. Minus, then we don't have any more s's, and the next derivative would be y prime of 0. Notice the last term is one derivative less than what we started with. So if I said, what's the Laplace transform of y triple prime? Well, that would be s cubed Laplace transform of the function, whatever the function is, minus s squared y of 0, minus sy prime of 0. The last one would be y double prime at 0. So the powers of s count down, and after the first term, the derivatives count up. 0 derivatives, 1 derivative, 2 derivatives. You should always end up with one less derivative than what you started with. All right, being able to do this is going to be helpful in solving some differential equations using Laplace transforms, so make sure you understand how this works.